topology. Arc, node, topology. What are topology? Spatial relationships. What is topology? Spatial relationships. So now we see orientation. Orientation is, for example, and A. This is its starting point, and this is its ending point. So this is starting point is 16, and the ending point is 17, and then you can see how this information is geometry, symmetry, or the shape, or so the table how it has moved. So this is R A starting node from where it is starting, that and ending node that is 17. I see here. Starting node is 16, ending node is 17. The same is with arc C. This is arc C, and now 17 is its starting node and its ending node is 18. So how do we store orientation information starting and now connectivity? So when we store the area information in polygons, polygons they are also made of different type of arcs and how they are connected. For example, this is our polygon B. So you can see these are this is arc 5. This is arc. So polygon B is made of three arcs. Arc 1, arc 5, and arc 3. And you can see the same information here. Polygon. So how many arcs are there? 1, 3, and 5. Now, if we look at this one, this is comparatively bigger one. This is polygon D, and this is made of arc 5 from here to here, arc 4. This is arc 8, and this is arc 7, and this is arc 12. So polygon D has been made using these arcs 4, 5, 7, 8, 12. So this is its special property, how these arcs are connected with polygon B. So this is a special relationship of a polygon with arcs, and this is called connectivity, and you can see from the table how it has been stored. Let's see adjacency, and you can see from the arrows that from which side or in which direction those arrows are going on, and how do we store that the adjacency or left right polygons. The example which I gave you, for example, what are the adjacent districts of Solo? So you can store that information. Here you can see, okay, what are the left polygon and what are the right polygon based upon arcs. And okay, if I say this is arc 4, from here, this is its starting point, this is its ending point. So arc 4, and its left polygon is C and its right polygon is D. Same thing is with arc 8. So arc 8 is starting from here. So its left polygon is polygon F and its right polygon is B, and that has been stored here. This table. So this is how you store topological information. It is so till now I have told you three types of topological information. So what is topology? Spatial relationships. Very good. Remember that. Okay. So first one is the topological relationship. First one is orientation. Say it with me.
Orientation.
Topological property. Orientation. Second, connectivity. Very good. Third, adjacency, which we have just discussed now. And the fourth one is containment. You have to remember that. What are those spatial relationships which we call topology, and you have to store that in your map. Okay, I'm just and you can see also the topological relationship in this model, in this transportation map here, that how these different stations they are connected with the different lines. And when I talk about in terms of data model, so that node or that point is connected with this red line, connected with that green line, and how it is making connection with other lines as well. So this is also a good example of topological relationship. How do we store that information in our database? So adjacency, you can also see how those districts are related with each other. For example, this is Clementi, so its adjacent districts they are Juro, it's so and then you can also see how different districts are related. Now, this is an example of containment. So containment is when some object is located inside of any other object. For example, here we see, okay, the red polygons, if they are, let's say, parks or the forest, they can be anything. So we see, okay, that particular district, Jurong East, it has those different type of green areas or the forest inside. This is the relationship which is called containment and how it will be stored into the database. For example, this polygon. So this is big polygon P1 and it contains P4. So P4, polygon P4 that is inside of polygon P1. You can also see island. This you also see one island because Jakarta have, I think Indonesia have a lot of islands. So when you want to store those island information using vector data model, so you will make use of that for the containment. Maybe on the sea, what are the different islands which are located within that particular sea? So this is like how you have to develop the data model for the solo or for the Indonesia. You also have to store that the special property of containment as well. So we also use another data model in GIS that is called spaghetti data model. So spaghetti data model, we just store point, lines, and polygons, but they are not, we don't store the topological information. It is just like the spaghetti model or the noodles. You all eat noodles. When you put those noodles in a plate, how does it look like? Are they connected? Your noodles are connected? Or each noodle is just separate. When you pick up just one noodle, this is separate. You don't eat noodles this time. So this is the example of like how do we make it like the spaghetti data model. So in the spaghetti data model, you store that information, but it is not connected. Each information is separate, but in topological data model, what we use in GIS, We also store information of topology on the spatial relationships because we have to make use of different analysis. We have to process that. We have to put query on our databases to find the answers of some complex questions that we have the problems in real world. And so this is also, some example of the topological data model. Points are stored there using their spatial information, and some, the errors depend on that slide. So in topology, in GIS, why do we store that topological information? Because we want that our system is efficient. We don't store redundant data. Redundant data is when you're storing same information again and again and again. So what it will make? It will make your file size bigger. When you will process that file, it will take more time to process. So remember, all the time in GIS, you have to make use of topological data model when you are using vector data model. So with point, line, and polygons, you will also store that the related, that the topological or the spatial relationship information. So two things: avoid the redundancy of data, and also you have to use the to get the answer of your queries quick. Okay, so these things we have just discussed with that. Now coming towards the geo database. So in geo database, you store information about points, lines, and polygons, maybe images, topology, and tables. So all that information that will be stored into a geo database or a spatial database. And how we use that in the GIS. So these are the example of different the feature classes. Maybe we make use of waters, lakes, rivers, streams, roads, railways. They all will be stored into the geo. For the non-topological data model, you will just make use of coordinates, but they will be not related, not the spatial. Okay. And the same thing is with the polygons and with the linear objects. And you store that geometrical information in GIS using shapefile. Because what we are storing, point, line, and polygons, that is geometrical information, geometrical information, and in geometry, we are saving or storing shapes. Okay, so just a description of that. So that's all for my side for the vector data model. So we have discussed vector data model. We store two types of information in vector data model, that is spatial information using its positional information, using coordinates or place names information, and then its attribute information using quantitative or qualitative data, and then we use topological information. So based upon the spatial relationships, there are four. One is orientation, second is connectivity, third is adjacency, and fourth is containment. So these things have discussed. You have to remember that maybe in tomorrow's lecture, if you are here, I will ask you again from you guys, what do we mean by connectivity? What do we mean by spatial position? Okay, thank you very much. So are there any questions? So do we have to ask another question from students now or we go with Dr. Nawaz presentation?
both can be. So if all students have any questions, please raise your hand. We have 5 minutes before we continue for the second session.
Or maybe you can ask question in Indonesia, so you can translate that.
Oh, oke. Jika ada pertanyaan dalam bahasa Indonesia, bisa dipersilakan. Ada pertanyaan? Silakan. Dari kanan ataupun kiri. Oke, kalau nggak ada nanti saja. So we will continue.
Thank you very much.
Thank you very much, Dr. Farzad. Thank you very much, all the students. That we have a break. And then I start 5 minutes. Then we have a 5 minute break and we continue after 5. By the time I will set the Thank you so much.
Ngapain, Pak? Ngapain? Agungmu, Pak. November. Oh, sekarang kamu tapi nek kalau sekarang di anu ramen pas pulang aja ya. Pulang mau. Kasih tahu ya. Oke. Masalahnya sudah nambah. Iya. Udah di Zoom ya? Sambut. Ini tentang YouTube gini. YouTube. Dan
Oke, pada teman-teman mahasiswa, nanti kita bantuannya ya. Tesis sebelum kita berakhir, ada setidaknya satu atau dua, tiga pertanyaan nanti bisa apa namanya menanyakan pertanyaannya biar situasinya hidup. Oke, bahasa Indonesia atau dalam bahasa Inggris. Udah kalau nggak bisa, kalau untuk belajar berbahasa Inggris bisa di apa namanya di uh, prepare dari sekarang. Oke, terima kasih. Ini ada break sekitar untuk bahasa Inggris. Nanti bila ada yang bertanya mau mengajukan jaring, nanti saya akan memberikan mikrofon ke
Ini ada finish. Ya, isinya. Ya yang jadwal itu saya hafal. Dan tadi yang ngomong mana? Dia nge-share jangan share presensi. Mana? Oh, yang verifikator yang sharing. Mau di-share? Kayak Pak Choi tadi tuh kayak itu. Ini gitu, tanda tangan ini kuliah umum dan setelah mengikuti kuliah umum saya di sini Pak Choi.
Okay, welcome. I hope you're going to do great and you have solved what Dr. Farha told you. She told you so many things. He said, I will not touch raster database, but she touched it. He has touched raster database, my database so many times. That's also a relationship. Okay, there we go. Raster data model.
Khusus saya mungkin Pak.
By the way, how much time we have now? It's a 1.5 hour lecture, so I cover in 40 minutes. Okay, I'll be not saying much, so I'll be brief, but I hope I convey you everything. All right. What I'm going to tell you today. Number one, what's the concept of raster data model? You already got the concept a little bit of the data model. So raster data model is not much different. It's also data model, but the difference is it's not 0.9 polygon. It's a fix. Okay? It's not 0.9 polygon. It's a pixel. When I say pixel,
Kamu ada geser sana, kena kamera.
I already simplified pixel. It's a pixel-based database. So there are some elements of raster data model that you need to understand. If you want to really work with raster data model, you should follow what are the elements of raster data model. I will cover that. Raster data structure. You learn about vector data structure. So I'll teach you about. Sorry, I forgot. I can't. I'm in NUS. No, I'm in UMS. Slow down, Nawaz. Slow down. All right. So raster data structure that, and I will cover how we can merge raster and vector. So what Dr. Farha created in the whole morning today, in 5 minutes I will convert into raster. Okay, we do it quickly in 5 minutes. I tell you how raster. There is it. Let me start with the concept. You see, this is something. What do you think? What is this? You can say anything what comes to your mind. What is this? What is this A? Do you think what is this A? Map, image, photograph? Say anything what comes to your mind. Okay, yes, this is something. Let me zoom in. Like Dr. Farha told you about your picture. Zoom in, zoom in, zoom in. At the end, what you see is this. So it was an image. To zoom in, we have pixels, and these pixels are representing all fields. So rather than point, polygon. In raster data set, in raster data model,
Balas juga pakai
you
laptop.
represent pixels by a pixel value. Are you with me? So rather than point line features, we use pixel and pixel value. So every pixel has some value. Can be quantitative, qualitative, categorical. That's another method. So there are pixels, both sides.
Siapa?
That's the pixel and pixel have value. That's how we kind of whole reality. That's the raster data model. So raster has a grid structure. For example, all images are stored in grid structure, and that's what
Boleh. Kalau sampai.
they are rows and columns. And in rows and columns are small boxes called pixels, and that's the grid structure of the pixels. That's how we store data. So basic unit of raster data model is pixel, or call it another name, cell. And cells and pixels have numerical value that makes raster data set, that makes raster data model. It is easier than vector data model. Do you think it's easier than the vector? It looks simple. So you have a picture, you have a selfie, all your features, everything is stored in small unit cells or pixels, and those cells or pixels have value, and that's your database. Now you relate all Dr. Farah conveyed to you the coordinate system, the position with it, spatial relationship, orientation, everything you can connect with the pixel rather than 0.9 polygon. That's it. That's all done. So we replace 0.9 polygons with pixel, and rest we do all the same. Okay, it's done. Clap. Actually, it's over. Don't go. I have few important things to tell you. Okay? Yeah. Don't go. One thing. So, spatial variation. Because in reality, the things are changing. We have different things and they are changing. That change is represented through all phenomena that's changing, that we call spatial variation, and that spatial variation is reflected in raster data model to a value, a number. So pixels have a rows and columns, they are grid in grid, and all pixels have some number. That's how we represent the real. Is it much different from vector data model? Yes or no? You said yes. No clap. Yes or no? Clap. Answer is yes and no. I'm also with you. Yes, sometimes yes, sometimes no. Let me tell you the detail. Here we see the real world. That's the reality. So, if Dr. Farah will store it, Dr. Farah will store it as a polygon or as a line or as an area. I'm not Dr. Farah. I store it like small cells or pixels. I store a value. For example, if there's something white, I call it 0. Otherwise, I have 1. Otherwise, I have 3. So these values represent the real world phenomena in the nature. Now, what we are doing in vector model data model, we are bringing in real world phenomena with the help of point line polygons to the database. Here, we are bringing the real world phenomena in small boxes, pixels, or cells with certain numerical value. That's the name. Dr. Farah, thank you very much. You made easy for me. I'm relating everything to your vector data model. So now I'm bringing, rather than 0.9 polygons into pixel, I have a numeric value and real world is equivalent. Is this easy or vector was easier? Do you think it's simple or vector was simple? Raster simple. Thank you very much. Well done. Raster is very simple. And raster is very effective, but vector has its own advantage. What's the wrong with the raster? If it's simple, why don't we always use raster? Why don't we stop using vector? Because vector give you aesthetic value, a real shape. When you store something in a raster, it always Z-shape. Line and polygons give the real phenomena a good shape. So aesthetic value is low. Processing is quick. Both have advantage and disadvantage, we'll see. So vector is important, raster is important, but these are the two data models we use. Both are important, both are useful. Both are have their advantage and disadvantage. So here we see precipitation distribution. And why we need this sort of data? Vector data model is mostly used for discrete objects. Dr. Farha explained the discrete object. Not changing, it's standing. If it's a building is standing for 100 years, the same building is a discrete object. But what about is a rainfall? Rainfall amount is changing. Precipitation distribution is changing. We have some distribution now, next year different, even month, even a day, morning, evening, midday, we have different precipitation distribution. So in reality, in real world, phenomena are changing quickly. Vector data model is very good for discrete objects, for aesthetic value, for shapes. But when the things are changing, we call it continuously, and for continuous changes, we need something real world update, something happening in the reality, update in the database now. Now you know there is some traffic density on road A, and our app will tell busy road, don't go that way, change. That's a real time update. Raster data is really for that. So we need now in GIS we use the combination. For example, we have elevation model. You know the dam? Digital elevation model? Yes. Okay, great. Do you know DTM? Very good. What is DTM? Digital terrain model. Then is digital elevation model. There is another DSS, digital surface model. These are the things on which GIS representation is built. So we create STEM, DTM, STM, all these things, and most of these DEMs, STMs, and DTMs are raster data set. But they store a huge data set, and based on numerical value, we can process them easily. So, as a real world phenomena, they are raster data sets. For example, we come across pollution. You have sometimes haze, Surkarta solos, haze, smoke, fog, particulate matter distribution, and you need to update real time. You need raster data set. These sort of quantities value you need raster and better. So, precipitation distribution, elevation models, particulate matter. These are few examples of real world continuous phenomena. They're continuously changing. Can you give me one more example of continuous phenomena that's changing? I'm really glad for the group who tell me one more example. Continuous phenomena that's really something changing. So we have precipitation, elevation, particulate matter, pollution. 3 examples before you. One more example from you. Hello. An example can be traffic data, can be flood, changing water distribution, etc. All these things, so all continuous phenomena. Reality is changing, and we need some sort of data set to represent the change in reality, and that's the raster data. Now we look at type of data. In GIS, what we use when we use raster data model, we need to understand this is very important. Different varieties of data that is we use and how we store. For example, we scan map. We have maps on paper. We hard copy map. They now use scan. Now you see all scan map on your apps, on your system, on your laptop, on your laptop, on your iPhone. All scan maps are raster data set. Your map captured from computer screen, you click store scan image is a raster data set. And you have all satellite imagery, satellite images, you know the a lot of satellites we are around. all data that is coming from satellite is raster data set stored in pixels, and we have digital models. These are all examples of raster data sets. These are all rows and columns of pixels with some value, and it's called raster data set. We can do both. By the way, my whole is slowly. These all images set activity. How we are getting all this data? And we have huge raster data set. We are not processing. So we have developed technology to acquire raster data sets. And we have required a lot of raster data set, and we haven't developed the method and technique and algorithm process recovery. We are only processing 5% what we require. So humanity is going far for acquiring and processing is lagging behind. So if you look at sensors, we have passive, we have active. You heard about LiDAR, you heard about sonar, you heard about satellite images. If you use the daylight and you capture the data of the Earth, Google Earth or the images, that's the active remote sensor. If you produce some energy in the sensor, then that's the rest. But how it is stored doesn't matter active or raster or active or passive, but it's stored as a raster data set. I hope you have still energy. I'm sorry you are listening to us from last 1.5 hours. I'm still see you have energy. And please give me for another 40 minutes.
Yan na sing wani ngaya, hindi juga.
And all satellite images you have heard about Landsat, you heard about Spot, you heard about GUI, you heard about images. They're from USA, France, Digital Globe, and from different companies. And they have bands. What are these bands? There are different layers of raster data set. That means they are grids, they are pixels. There are different layers of data sets. And the highest resolution you see here, Dr. Farha has talked a lot about resolution, so I will not go. GUI has 0.4 to 1.6 million resolution. That means you can GUI can pick the object in this range. That's the resolution, and it's a spatial resolution how the satellites are fitting and they are providing the score. It's a temporal resolution. So you have spatial resolution when you pick the piece of the space. Go by 4 meters, then
Tunggal dokter Nawaz. Aku hari ini kalau ingin pulang, udah minggu. Masih ini di pendek dokter Nawaz. Tinggal sedikit. Kamu tengok tas. Oh kan, lengganya.
Oh, 85% last data set is spatial and temporal, and we call it geospatial temporal. They use the different dimensions, 0.5 by 0.5 meter. 1 by 1 meter, 0.5 by 2.5 meter, 5 by 5. So some is coarse resolution, other is high resolution. Dimension goes smaller, the resolution goes higher. Simple is that. Where we can use this data. If you are GIS student, you should know there's a lot of data around you, cost data, but here you can use. Some you can use in emergency service. To have an idea that what should be the resolution. But emergency services, 1 by 1 meter. So different applications. I'll cut short. We need to develop an understanding which data is applicable where. Tomorrow you'll be doing the research. Tomorrow you'll be developing application. Take a message, online message. First thing, to put some time, understand the resolution, both spatial and temporal, and then look what is where required. Then start your work in the research project and that's very important. They start with looking at the resolution. Another thing important to know in raster data set is that that is something with the light range. So in high school physics we learn about different wavelengths. That's the wavelength in light. there is this visible range. So most of the remote sensing data actually comes in different band, and this visible band that comes forth, and anything you come across in African band one band three, so nothing is the range of a satellite of a specific range of wavelength that is band. Band is a wavelength. For somebody asking the question, if I ask the question then network wave, so band is a particular big, but again down is a row and column
Dari
and is a
pengalaman.
fixed value, is a value there. That's how the information is stored. And that's what it multispectral information. We are capturing different wavelengths, 1, 2, 3, 4, 5, 6, 7, 8, and different segments are capturing. Here we have multiple segments, remote sensing system, and we have infrared and red range. That's the light wavelength that is learning light range. From light range to a different band, and we do that band process. Because it's a big story. Now I give you an example, and we understand this band. That's land is a center. And answer data is free. So it's a free, you can download, anybody can download the data, how much you want, you can download, it's free now. And Landsat has, it was launched by NASA. Landsat has different vendors, the link, landsat.usd.gov. Maybe you are interested and you want to try, go to this link. Download any data of your area, of your country, of your region, your city. Look at the pixel, look at the band, and in Landsat, different, we have different types of bands, 8, 9, 10, and now we launch 4 Landsats. We started and 23, we are still at Landsat 9, it will go until 2040, and it's a free data. Download the data. It's a free, make use of it. Look your places, analyze, because it's a raster. Use the raster data model before playing with data set. Learn about raster data set and make use of it. And so there are different bands. And there's another satellite spot. Spot have 1, 2, 3, 4, 7, 8 spots. And few of the data sets here are also free. It has also different bands. So it's going on. To download and play and make use of this data set. The whole world is making use of this free data set, playing, learning, and building different types of applications. UI is another one. It's going to be free in few years. So it has different band ranges. I will just touch on what is it. That's also providing you raster data, and you can make use of modest data set. 36 spectral band here, a lot of band that means huge data and huge data set. You can see, even if you put your shoes outside, you realize that you see it's a shoe 12 number, 42. So that sort of thing now we are doing lots of non-visible. That's how the patches, spatial resolution, small patches, then we join together. Now we come to the model editing. You touch on them, what is it? It's nothing more than a matrix of rows. It's a table. It's also a table, but in this there are pixels, and these pixels have value. 2.4, 2.5, it's a height, height. And based on these values, we generate and this is this is a digital elevation model. So behind data set is nothing more than a table and some numerical values. So just like I think table in back data, right? Then itu wajar yang dulu. Dia mesti penting. Ini hidup terus berarti.
Kalian Pak Wahyu. Benar.
Makan
Yang tadi ini nama Pak Wahyu. Berbanding defensi yang kan. Banget. Ya bangun niki. Wow. Kan pena nyiapinnya. Dek, jangan kesini dek. Ada lagi dek. Oh, masih buatin kamu. Oke. Yang pertama dia harus untuk
Okay, I think I got 15 minutes more. I have gone through slides quickly. I promise that I will slow but or require too much time so I can make sense of what I said up till now. So, the digital animation model is a type of raster data set, and what you see in front of you is the row and columns, pixels arranged in row and column, and they have certain values. Those values will implement the animation model. There. So, then how it is stored, the matrix, row and column of pixels, and they give you information 2D and 3D, and it's called actually 2.5D because it gives you information of height. It will give you information, you can calculate the width, length, and height together. So it's a 3D data set. Then we call it, then it's a 2.5D or 3D data set, but it's a rows and columns. It's very, very analyze as compared to vector data set, all images, all bands, anything to discuss in raster data model is the metrics of rows and columns. Right? And when you give a spatial coordinate, it becomes spatial. So you have cache spatial information, rows and columns. How we collect raster data on Earth, and then image bring you from the sky. Here is the tool, GPS, total station. You can generate, you can use LiDAR, you can use drones, you can use so many instruments on Earth also, and you collect this raster data set. But the data set, we have certain values, and you can also predict. And you generate the previous service. So that will give, if you have point information, then your point information, you take it between the average. All your price algorithm. So that's the beauty of raster data set. That interpolation you can generate services, but that is not possible in vector data. But they see them generated by using aerial photographs for airplane. Well, it's photogrammetry. Here you see the LiDAR image. Here you see the inside. They are all new technology to develop raster data set. By the way, in GIS, the most technology now we are developing is to acquire raster data set. It's easy and it's a future. Most of the GIS will remain with the, it will go with the raster data modeling and raster data set, raster data analysis. Okay. Digital animation model, what is this? Here I provide digital animation of the highest resolution field. This is a matrix and a numerical value in that values and matrices. And cell size to fix your cell. In raster data set, cell size gives you an idea of your spatial resolution. And have a small size cell, large cell size, even larger, and that goes to same scale thing. So here the cell size give you the raster spatial resolution. Cell size can be smaller, can be higher, and when you need precise location, you go with cell size smaller. The smallest cell size will give you the precise, most precise location. large cell size will be to the coarse resolution. And that's because spatial resolution. When raster data spatial resolution is basically cell size. Now you give an idea of scale. If I go back, go back outside this global level, I can focus all of you. I can see all of you together. If I come here, I see all of you. If I come here, I can't see all of you. I can see few of in front of me. Now I can have a detail of Dr. Farha. Detail is high. I am closer. Going back, my view is increasing. Come more, but your detail increased. Come close, your less, but your detail increased. That is what I can and it has to do something with scale. Either is math, either is a vector, when it comes close, your size structure, your core that is higher. That's not and spatial resolution is basically based on cell size in raster data. Okay? So what is spatial resolution in raster database? It's a cell size. And temporal, how long it will. Then you can see that. That's 80 meter depth. It's a 10 meter depth. It's a 3 meter depth. That means the pixel size is 3 by 3 meter. And you see the more detail. Your hills, troughs, heights, more information. And your IFOV is increased. You're closer. So you're closer, your cell size is different. That's a spatial resolution. I hope you got the idea of spatial resolution. I hope you got the idea what is raster data set. I hope you got the idea that it is like vector data model, but it is not what like column is pixel based or cell based. The basic thing, data models is the same. To replace point line polygons with a pixel, all other things for Dr. Nawaz will be apply on raster. But raster, quick, easy to obtain. So different images have different resolutions. What are the scale? Am I talking about spatial resolution or temporal? Any idea? I said different images have different resolution. What resolution I am talking about? Spatial or temporal? Spatial or temporal? No, when I say resolution, it can be any. It can be spatial, it can be temporal. So, resolution of satellite images can be both. Spatial, cell size. Temporal, how long, how frequently it's visiting the Earth and capturing the data. After a day, after an hour, after a month, after a year. That is temporal resolution. So that goes to the temporal, spatial, and temporal resolution. Here see, spatial resolution, cell size, and temporal resolution, June 1, 2023, 60 days. So this particular satellite we are talking about, it goes around the Earth after every 60 days. That temporal resolution. So time resolution and space resolution, spatial and temporal together make what type of resolution? Spatio-temporal resolution. And in raster data set, we normally deal with spatio-temporal resolution. In spatial, if we have volume and we add time, how many dimensions are there? If I talk about dimension, how many dimensions are there? 1, 2, 3, 4. 4. Thank you. I come for this group now. And then temporal. So 4-dimensional data can come from the satellite because they have temporal dimension. All right. Then the rest is all like that. So resolution of satellite images have a spatial resolution, have a temporal resolution, and the third resolution satellite images have a spectral resolution. Spectral goes to spectrum, to light, number of bands. So satellite can provide you only one band, one layer. Other 2, other 3, GOI will provide you 16. So spectral resolution highest we have right now is GOAI, that's spectral resolution. So there in raster data deal with rather than 2 resolution with 3 resolutions, and those are spatial, temporal, and spectral resolution, the number of bands. That world is changing. Technology is changing. And we are scanning, we have almost scanned every part of the earth, and we're scanning every part of the earth now, every day, so many times, I don't know. Tomorrow, in 2050, you may be scanning the earth 10 times in a day. So do you. Then you know who is going where. Still we know through apps. We know who is going where, we have coordinated all this. So the things are changing in GIS, and we are getting raster data into all 3 resolutions, and we are getting a lot. There you see the different resolutions, wavelength, band, and when you say meters, it's a spatial resolution. When you say the wavelength is a spectral resolution. When you say bands, spatial resolution, right? Spectral and spatial resolution. That's the idea. What do you see here? It was a image downloaded from Google Earth, right? And then we identified the pixels, and we gave different pixels a value 1, 2, 4 till 31, and each value have a characteristic color. So it's a giving a phenomena. It's giving the different land cover types of Singapore. So we had pixels. We can ourselves assign a color to a value. A value can come from the satellite, or you can assign a value to the pixel as such. That's the beauty in raster data. You work, intervene yourself, and create the application what you need. You already have a scan, you have a pixel, you have matrix, we have everything done. Then you intervene and develop. So here is the intervention, and we have given different colors, and there's a land cover map of image. So that's the last slide, and I need your kind attention. Now I need your kind attention. I'm leaving few slides. Hello. Somebody is sleeping, get up. I need your kind attention. It's the last slide for me to look at this carefully. What is this? It's a simple non-forest and forest area. That means there was a area satellite image. We wanted to know how much forest is there and how much non-forested area. We are not interested in anything else. What we do? We already matrix of rows and columns. We have value. We intervene and we call one thing 0, non-forested we call 0, and we give all other one value. So it's a 0 and 1. We classify it into two. Want to know forested and non-forested area. Just where is the forest, where is not a forest. We need that. We did that in raw application. So 0, 1, 0, 1, 0, 1. It's a classified, supervised classification of image. We have forest area and non-forest. That's what we do with anything. But the most important thing, why I need your kind attention. 0, 1. How long you think 0 have been there? And 1 have been there. 0 origin from a term sifar. And sifar is an Arabic word. It's a 0, 1, that's you call a bi-level map. Another term for it, binary. All computing, binary, you know bit and byte. But look at the base. You know this person? Any idea? It's Musa al-Khazmi. Musa al-Khazmi, a Muslim scientist, when 8th century, he started the application of sifar. Sifar means 0. Original term is sifar. It's still in Urdu, Hindi, and Sanskrit, so many languages, but sifar is Arabic word. 0. Then he started 1. Image is stored here 0101 forested area, non-forested area. What I say to the Western world, return our binary 0 and 1. And think about your all technology. We gave you the 0 and 1. Do I need to repeat? Or do you understand what I said? That's the origin of application of 0 and it's Musa al-Khazmi. We never know, never taught to us. It's the starting of technology, the binary bit and byte thing, all is on top of this. See, first application of 0 we see Musa al-Khazmi's work. Still, we have a lot of technology, all these things, 0 and 1 is binary, that's how it's stored. 0 and 1 is forested, non-forested area. And what I say, what we can, I say, oh, what thing, what happened to us? We have gone over science, now we are giving the leading. He started with this, and it's a Musa al-Khazmi. Nobody can deny. All historical books, everything been quite. So that's the base where I would say the raster data set started in 8th century. It's not new. There were no satellites, but that was the concept of 0 and 1, right? That's how we are storing, how we are talking about bit bytes, and that's how we are doing all this. So if you go to the basics of anything, it doesn't matter. It's a vector data set, it's a raster data set. Stop for a while, think, what is this? The things are not complex. It's a one matrix and then have a value, and rest is the application, what we see, what we visualize, visualization and all this thing. Tomorrow I'm talking about spatial data visualization also. So what is base? It's the storage of a numerical value, and 0 is given by us. So I'm very proud of Musa Kazmi, and I claim that give back us 0 and 1, and then what's the value of your technology, your whole computing system. On top of that, thank you so much. That's all for you. If you have any question. So I hope I finished time.
So to all students, if you have any questions, please raise your hand.
Oh, okay.
From the right side, from the corner, from the front, or the left side.
From the left, from the right, from the back, it's a special relationship, okay? From to left, right relationship. Ecology. Okay? Alright. If there is no question, remember bit byte binary is the beginning from the Muslim world. The rest is on top. They don't have any system if you say stop doing this. If you have copyright on 0 and 1 bit and this binary thing, bi-level thing, if you have copyright on this, we announce, why don't we think we can say it's copyright, it's no copyright? Into your technology and Western world. Thank you very much. Have a good day. See you tomorrow. I hope I will start tomorrow. I don't let Dr. Farha start. She can use it almost 2 hours. Thank you so much. And see you. Sorry, I have to be quick. I promise not to be quick. That's how you.
Okay, thank you so much for the Nawaz and Farha. So good afternoon to all, to all my students. See you tomorrow.
They are happy they're not going, so I can go to the other slide. I will not.
Ya, ya. Oh, sih ini bola.